Okay, hi everybody. Well, I've been working on this project, I guess some of you will know it. I'm trying to write a compiler for TyCL, and I call it TyCL as a typed common language. What I'm going to show you today is, actually I'm going to show you the compiler working. The first thing is, well, does it actually work? I mean, does it make the programs run faster or not? So before I say anything else, I'm just going to run a small program just to get you started. Right? Use this. Okay. You heard me, right? Okay. I'm just going to write this program just to, like the control, right? It's not going to do anything at all, and this is just for TyCL. What I'm trying to explain there is, you know, how much time TyCL needs to boot up and shut down, right? So you get the idea. So I'm going to run these tests. I'm using TyCL 8.6. So as you see there, this is the time that it uses just to start and finish, right? So remember that when you're going to see the time for TyCL, you have to subtract that amount. Like, what's that? 13 milliseconds, I guess. Now let's see the program that I want to run. Just a small program. It's this simple. It's just a cycle, counting down, and that's it. I don't want to do something more because then you're going to try to analyze what I'm trying to do. So this is kind of simple, right? Okay, so let's try that program with TyCL. It's counting down 1 million to 0, and it uses about 1.12 seconds. Now I'm going to compile the same program with the compiler TyCL. And we got it there. I'm going to show you later all that stuff. Don't worry. Okay, actually, I think I have to run it again so you can compare. This is TyCL, and this is TyCL. It's about 20 times faster, something like that, and close. But actually, it's not fair for TyCL because if you see the program, actually, I'm working on the global frame, you know, the main one, so it doesn't get the chance to bytecode the code, right? So I think I have another version here, which is this. It's exactly the same program, but just inside of the procedure, so you can, you know, try to bytecode the code and just, you know, run it. Okay, so let's try it again. Here you go with TyCL. Actually, we should try with TyCL first. There we go. Okay, it's already compiled. Forgot the time. Okay, it's about 24 milliseconds total. That's now. Let's try with TyCL. Here we go. This is the one, right? 39. So it's not that fast because now TyCL is using the Python compiler. So okay, actually that was impressive. TyCL is really, really good actually. So we are running here just a regular program, TyCL syntax. I'm not using anything new about TyCL. This is just a regular TyCL program. I'm using the worst case scenario. We are not using any types of the variables. He's not trying to guess anything at all. He just runs and tries to figure it out everything at runtime.
So that's the thing. So the question remains, does it work? I think it works.
So I think it works. Now it's how? What does it do? What does it do? So this is the architecture of the compiler, just like a regular compiler. You know, the source code goes from one side and give us a machine code at the end. But the difference is TyCL tries to parse the whole code before going further. I mean, it doesn't do anything dynamically in parser, right? You have to understand everything. And that means if you have a block of code, it goes inside and tries to parse it and try to compile it. So it parses the whole thing, right? We're trying to avoid any dynamic evaluation. TyCL could have, that feature. If it finds something that you have to be dynamically evaluated, it doesn't do it right now, but I think it could possibly do it if it have to. The other thing is, once it gets the whole source code is all parsed, it generates binary tree, ASD or an abstract syntax tree, and tries to detect the types. Well, if you write the types using the TyCL syntax, well, actually that's a good thing, because it knows already what types that you're working on. But the idea is, well, with time, it doesn't do it quite nicely now, but with time, I guess we can guess some types when you describe your code. So if you use that information, it can generate a specific machine code, for whatever you want to do, right? Right now, it just generates for Linux Intel, x86 and 32 bits, because that's the machine that I'm working on. So that's one. I mean, that's the most obvious explanation of why it runs faster, is because it is not doing anything dynamically in terms of understanding the code that you're trying to give it to run, right? So that time, it's just compile time, not run time. Okay. Now the other part is about memory, about how the data is organized in memory. Because if you organize it in a simple way, you can have better performance on it. So, for example, the idea is we have to avoid using dynamic memory allocation as much as possible, because that's kind of slow, right? So that's one of the main things. Well, the explanation of why this is the the memory model for the values. Actually, we have two memory models right there. The core of anything is the white stuff. It represents the data, the type of data, there are some flags over there, and this reference counting value there. It is not the same as reference counting in TyCL. It's used if you are referencing one variable to another one only. So the idea here is try to avoid, copy and write. So we're going to have to check the reference counting every time that we are going to use memory or we are not going to use memory. So you have to increase the counter, check the counter, goes to 0 or whatever, then you can freeze memory. The idea is not to allocate memory dynamically as much as possible. So the whole thing is the value, and it's wrapped in a variable structure. I didn't put the descriptors over there, because that depends on the envelope that is holding the value. This is real different from TyCL, as long as I know, because in TyCL
these two guys are separated. In the variable part, it has a pointer to the data, which is the TyCL object. If I'm not wrong, you can correct me, but I think it's that way. I'm integrating the whole thing. Just avoid that pointer. So I don't have to use reference counting for the value itself. Right? Now, that means I have to provide a place to store data on every operation that I do on the data. Right? Okay? Now, before I go any further, these little 4 bits over there are this. And that tells the compiler what type of data, what to do with the data over there. For example, if that data is constant, you cannot change it, obviously. If the data have a defined type, you have to put something there with the same type or something compatible with the type. For example, if that data is defined as an integer, you cannot put a real number or floating point number. That would be illegal, right? The other part is if the data is static or not. So if that particular value is really a pointer to the real value, which is contained in the raw data, well, that's a pointer. And that tells the compiler, okay, should I free it? I am able to free it or not? So sometimes that data over there is generated at compile time, so you cannot free it because it's not a dynamically allocated memory. And the last one is, it means that the data is not there, the data is somewhere else. What we have there is a pointer, so it knows what to do with the value. Okay, now, that was the value was, was package of the payload. This is the description of the type. Every value has a type, even if you don't write it, internally it has a type. So right now we have the description of the type like this. This is a set of functions that operate over that data. That's exactly what we have right now. For example, we have functions to go and find an index inside of the data or get a range, or in case of objects, for example, how to manipulate the members if the data has members inside. And this part is for cross definition or function definition, so how to manipulate, how to call that function over there. At the end, this description is just part of the type descriptor. That's the common part. Every type has that part, but not every type has this part, which is specific to each type. It has internal descriptions about the type. For example, well, it doesn't work like that, but think about an integer, a 16-bit integer. That part, that 16-bit, the size, could be described inside of the internal data, so it knows where to find it if needed. So that's exactly the description of a type. The other part is all the types, all those descriptions are put in the table next to each other, So that's why we can have an offset here. Those offsets are always reference to, I'll see it later, to the beginning of the table. So it doesn't matter if the table moves, if we change the reference to the beginning of the table, get all the types. So at the end, this is the total representation. We have the data here. If you're working with a variable, well, we have more data over there, but it has a type. The type has an offset to the types table. It could have raw data outside of the value by itself. That configuration gives us, well, a possibility, which is there are some types that can have more values than just, like a number, like a list, for example, or an array, right? So in case of an array, we can define arrays in TyCL. like this, for example, you are defining type A as an array of 3 elements, but you are not saying what type are the elements of the array. So with this description, what it does in memory is something like this. These little boxes are values by itself, so it gets a reference to the array, in this case 3, and each one is a value by itself. But if you use a type on the array, we don't have to keep this information. Because now the array knows the type of the data that it's working on. So now we have in the descriptor of that array the subtype, and we don't have to store the rest of it, just the data by itself. That means we use less memory. We maybe access faster because you're working with less memory at the end. So if you're working, for example, with the structures, well, you will have an integer here and a floating point number over there, following the same conditions as C programs. So the whole idea of this is you may able to interchange data between TyCL and libraries within C, which is possible with TyCL actually. Well, the other part is about the execution frames. When it goes and tries to process or run a procedure or function, what it does actually creates a frame. And within the frame, well, it creates the parameters. If the parameters are required, optional, name it, or flags, or the args list in case of dynamic parameter passing. But also it allocates space for registers. That means that that procedure, it runs without using any more memory. Because as we are compiling, we know exactly how many registers do we need to process that procedure. So it just does one memory allocation for the whole thing. And that's it. It can process all of it. Unless it needs something extra like this, right? Well, we can't, know in advance. Not always. So that's the other part. There we go. This goes fast. Right now, it's a working prototype. It has bugs. I mean, the code is a little bit ugly, but it works. I'm going to show you a demonstration. Another one. This is a little bit more interesting. I wrote a little program that calculates prime numbers. Yeah. Oops. Okay. Try to put it. It doesn't like really bad, but just for testing. We are going to try to find how many prime numbers are from 0 or 1 to the number that I'm going to give to the function. So it goes, from 1 to that number, and then it goes from 2. Try to divide, and you find something with a module. Where is it? Right here. 0 is because.
TyCL will get much better performance if we raised your expression.
Yeah, a lot. Yeah, actually, a lot. Yeah, but we can test it anyway. So that's it. It just flagged it. It's not optimized. It's not the best algorithm, but it's just for testing. It does the whole thing. I mean, it checks the whole range for each number. And if you find something with module 0, you flag the number, add it to the total. That's it. It's actually not like a big, difficult thing to it's a good function to test, I guess. All right, so put this here. What do we do first? We call it TyCL. Let's go with TyCL. Okay, now it's running with TyCL. But the problem is, as Andy said, we should have put some braces on that expression. Because those braces cost a lot. I mean, a lot. I have to stop the program there because it's going to take like 3 minutes and a half to complete. So we don't have that much time. So let's change it. There we go. Let's go down. Where's the expression? Ah, right here. It's okay? Good. Let's do it again. I think it's about 14 seconds. Ah, no, I was right. Around 14 seconds. All right, let's compile it. Times equal. I think this is going to give me an error. Yeah, because of the braces. Because in TyCL we don't need that. It's going to interpret this as a string. It doesn't like that. Right? You don't need that in TyCL because it actually parses everything. Right? So what it says there, okay, it's saying that there's a string there that I think you're right. This is the other part that TyCL does. Oops, just 10 seconds. I'll try to get better errors information, so it tells me exactly the line and where the error may be. So, okay, it's easier to change. So let's take it. Go. Let's compile it. Let's run it. Good time. It was 14 seconds, right?
Yes.
Okay. It's 1.9. And the thing is, we are not using the full potential of TyCL because we are not using the types. We are not expressing the types in the code. And I did it because, you know, if I put the types, TyCL wouldn't run it. Right? So it's fair, you know, to have the same common base. Okay? So as I told you before, the information that I got over here is actually, I put it there. I can show you the processes that I showed you before. The parsing process, the word code generation, and the machine code generation.
Andres, can you take the rest of the demo maybe to a BOF tonight? Because we're out of time.
No, actually I'm done.
Okay.
It's just showing you this, just to let you know that's all. This is the abstract, the parser result. Okay. This is the word code generation. And if you want to see, this is the assembler that it generates. And I'm not using, I mean, it has the assembler integrated in it. Actually, it doesn't need another program to assemble the code. Which is good because I can do a lot of things, weird things. And that's it.
We need to get the next speaker. Thank you, Andres.
Yep.
Our next topic is